Welcome back. We're going to continue on number 4 for pre-calculus cumulative review. The next rational function we have is q of x, x minus 1, divided by the quantity x squared minus 9. So again, we'll analyze the entire rational function first, and then we'll fill in the so-called boxes. So we're going to look for candidates for zeros. That's when the numerator is equal to 0. So our candidate is when x is equal to 1. Vertical asymptotes is when the denominator would go to 0. And from before, as before, we find that it's x can equal plus 3 or x can equal negative 3. We look at our long-run behavior, where the limit as x approaches 0 to find our so-called horizontal asymptotes. So the limit as x approaches actually plus or minus infinity. We've got x minus 1, x squared minus 9. So as x gets very large, this is going to approach, the top will approach just x, the bottom will approach x squared, which means the entire function ends up looking somewhat like the function 1 over x, and as x goes to infinity or negative infinity, this approaches 0, or the line y equals 0, which is the x-axis. And then we look at so we check for candidates for holes. Again, we don't have a conflict between the zeros and the vertical asymptotes, so there are no candidates for holes. So number of zeros, again, we have 1. Number of asymptotes, vertical asymptotes, we've got 2. So-called horizontal asymptotes is just 1 at y equals 0. And number of holes is 0. Moving on to the next one. So here we have r of x. So we'll look at zeros first. Again, zeros come from the numerator. So our candidates become x is equal to 3 or x is equal to negative 3. We look at our vertical asymptotes, or candidates for vertical asymptotes, from the numerator. That is when x minus 3 equals 0 or x is equal to 3. And then we look at our long-run behavior. So the limit as x approaches plus or minus infinity of x squared minus 9 divided by the quantity x minus 3. So as x gets very large, the negative 9 and the negative 3 will become insignificant, and this simplifies to x. So here we have what's known as the slant asymptote. As x approaches large values, either positive or negative, the graph will approach the line y is equal to x, approximately so. Now, I'll do an aside here. This is kind of the quick way to do it. It might actually approach some other line that's parallel to y equals x. To be exact, you'd have to use long division. And here's a quick example. So I would divide x minus 3 into x squared minus 9. And let's do long division. X goes into x squared x times. So x times x is x squared. X times minus 3 is minus 3x. We subtract x squared minus x squared is 0. Minus 9 minus a 0 here would just be minus 9. And then we've got nothing minus a negative 3 gives us a positive 3x. Then how many times does x go into 3x? And that's positive 3. So 3 times x is 3x. 3 times minus 3 is minus 9. And we've got 0 as a remainder. And our quotient, when you divide x squared minus 9 divided by x minus 3, you get x plus 3. So technically, this is the actual slant asymptote. Notice it is parallel to y equals x. It did take me more work to find the exact slant asymptote. So you'll have to decide if you're looking for the exact slant asymptote, or if you're just looking to graph this very quickly, you can just find the limit as we did up here. this is a little bit more exact. This is pretty good for this type of question because all we're looking for is the number of horizontal asymptotes. Obviously, this is not a horizontal asymptote. So for this one, we will have 0 horizontal asymptotes. Let's go back to the number of zeros. Well, here we have a 0 conflicts with a vertical asymptote candidate. So that will become a hole at x equals 3. So we'll have one hole. We will have no zeros, and we will just have one vertical asymptote at x equals -3. And I'm going to stop there before this video gets too long.